The topic of this video is to determine a graph's symmetry. When you hear the word symmetry, just think about your home or decorating, where symmetry, things that are symmetrical, are balanced, they're identical on two different ends perhaps. So we're going to talk about how a graph possesses symmetry, and there are three types of symmetry. A graph can be symmetric about the x-axis, about the y-axis, and about the origin, or it can have no symmetry at all. When we say that a graph is symmetric about the x-axis, this means that the part of the graph above the x-axis is a mirror image of the part of the graph below the x-axis. That is, if we reflect the graph across the x-axis, we get an identical image. I have on the screen a sideways parabola that goes through the point -4, 0, -3, 1, -3, -1, 0, 2, 0, -2, and in general, if the point xy is on the graph, the point x -y is on the graph. But notice that the part above and below the x-axis are identical to each other, and therefore we say it's symmetric about the x-axis. A graph can also have symmetry about the y-axis. A graph that is symmetric about the y-axis means that the part of the graph left of the y-axis is a mirror image of the part of the graph to the right of the y-axis. That is, reflecting the graph across the y-axis produces an identical image as shown. So I have this graph that goes through the point 0, 1, 1, 1.9 we're approximating there, but also notice that -1, 1.9 is on the graph. Our intercept occurs at like 1.90, also -1.90. We see this point 30, -3, 0, 5, -2, -5, -2 are some of the points on this graph. So in general, we can state this, that when we have symmetry about the y-axis, if the point xy is on the graph, the point -x, y is also on the graph. Then we can have symmetry about the origin. A graph that is symmetric about the origin means that the part of the graph left of the x-axis is a flipped mirror image of the part of the graph right of the x-axis. That is, reflecting the graph along the x-axis and then the y-axis produces the same image as shown in this figure that I have on the screen. Another way to think of this is that when we rotate the graph 180 degrees around the origin, the graph is unchanged. So I have this graph that has some points. It goes through the origin. It goes through the point, I'm going to approximate this, like 1.5, -6, and then -1.5, 6. Goes through the point 2, -5, and also -2, 5. It goes through the point 3, 9, and also -3, -9. So in general, to be symmetric about the origin means that the point xy and -x, -y are both on the graph. So I have a screen here that just shows all three types of symmetry. Symmetry about the x-axis. So notice that xy and x -y are both on the graph. So that means that the same x value corresponds to the y value and also its opposite. for the x value in the domain of that relation. If the graph is symmetric about the y-axis, then the point xy and negative xy are on the graph. So that basically means that opposite x values have the same y value. And then if a graph is symmetric about the origin, then the points xy and negative x, negative y are both in the graph. So this means that the opposite x values have opposite y values. So there are tests for symmetry for equations in x and y. We can certainly look at the graph to determine what properties it may possess, but algebraically we can perform 3 different tests. To be symmetric about the x-axis, when we substitute negative y for y, if we get the same equation, then the graph has this symmetry. To be symmetric about the y-axis means that substituting negative x for x yields the same equation. To be symmetric about the origin means substituting negative x for x and negative y for y yields the same equation. Because keep in mind how the points are related. On the symmetry about the x-axis, we saw that xy and x negative y were both on the graph. To be symmetric about the y-axis, we saw that xy and negative xy were both on the graph. And to be symmetric about the origin, we saw that xy and negative x, negative y were both on the graph. So in example 1, we want to determine if the equation is symmetric about the x-axis, y-axis, origin, or none of those. So we first test, is it symmetric about the x-axis? And that requires us to replace y with negative y. So we'll replace y with negative y to get negative y equals x squared plus 2. Then we solve for y to see how it relates to that original equation. To solve for y, we have to multiply or divide by negative 1. And when we do that, we get y is equal to negative x squared minus 2, which is not the original equation. So this means the graph is not symmetric about the x-axis. To be symmetric about the y-axis, we want to replace x with negative x. So we get y is equal to, in parentheses, negative x squared, then plus 2. But when we square negative x, we just get positive x squared plus 2. This is equal to the original equation. Therefore, this equation is symmetric about the y-axis. And to check if it's symmetric about the origin, we would have to replace x with negative x and y with negative y. So we get negative y is equal to, then in parentheses, negative x, then we square that plus 2. Simplifying on the right, we get negative y is equal to just x squared plus 2. And then we have to divide by negative 1 to solve for y. This gives us y equals negative x squared minus 2. Again, that is not the original equation. So the graph is not symmetric about the origin. And then another example, we have y is equal to x cubed plus 4x. So we want to check the same 3 symmetries. To check the x-axis, we will replace y with negative y to get negative y equals x cubed plus 4x. When we divide by negative 1, we get y is equal to negative x cubed minus 4x, which is not the original equation. So that means that the graph is not symmetric about the x-axis. To check symmetry about the y-axis, we replace x with negative x. So we get y is equal to, in parentheses, negative x, and then we cube it, plus 4 times negative x. Negative x cubed is actually negative x cubed, right? When we cube the coefficient of negative 1, we get negative 1. Then 4 times negative x would be minus 4x. So this is not equal to the original equation. So that means this equation is not symmetric about the y-axis. And then lastly, we check symmetry about the origin. So this tells us to replace x with negative x and y with negative y. We get then negative y is equal to negative x in parentheses cubed plus 4 times negative x. Simplifying on the right, we get negative y is equal to, well, what we just saw in the previous illustration. This would be negative x cubed minus 4x. And so to solve for y, we divide by negative 1. Therefore, we get y is equal to positive x cubed plus 4x. And note that that is exactly our original equation. So therefore, this graph is symmetric about the origin.